All right, so today what we want to try and figure out is how in the world, because again, we've talked about how to find the areas of triangles, squares, rectangles, parallelograms, trapezoid, rhombus, kites, and circles. So we've talked about lots of different shapes that we've been able to find what the areas are. But now those are simple because a lot of them you've seen since you were young, and they only have limited amount of sides. They only have like 4 sides. So we want to think about, okay, well, what happens if we're looking at a polygon that has multiple sides? Okay, so more than 4 sides. So if we're going to look at this hexagon, number 4. So we're going to use this one as an example first. Okay. And now the reason I want to work with a hexagon is because we want to be able to see. Or sorry, that's not a hexagon. Mr. Kiefer can't count. That is an octagon. Wow, good job. Sorry, number 5 is the one we want to work on. My apologies. Okay. Because a hexagon is essentially, it's an even number and it's a step up, and we want to figure out, okay, well, how am I going to be able to find the area of this shape? Okay. And so please know that what we're going to be doing, right, is going to be using regular polygons. Who remembers what a regular polygon is? What does it mean for a polygon to be regular? Anybody? Right, so remember that a regular polygon has all sides and all angles congruent. Okay? So what that means is for our little hexagon over here, this side, this whole side, this whole side, this whole side, this whole side, and this whole side are all congruent. And it also means that this angle, this angle, this angle, this angle, this angle, and this angle are all congruent. Okay? That's what it means. So if I want to figure out, well, okay, how can I find the area of this thing? We know how to find the perimeter, right? So if I imagine that this has a side length of S, then so does this, and so does this, and so does this, then so does this, then so does this. Okay? So I know for the sake of this thing, the perimeter of this guy is just simply the number of sides times the length of each side. Okay? And this is, so n is number of sides, s is side length, and p is equal to perimeter. Okay? And that's good and all. But how does that help us with the area? Okay? So, so now we want to look at, well, I can't really tell what the area of this thing is. Yes, I've got the perimeter, but how do I figure out how many squares can fit inside this thing? So what we're going to do is we're going to try and break this thing up into different types of shapes. So we're going to try a couple of things. So I'm actually going to erase all this. Okay. And we can see that obviously the center of this guy is right here. Okay? So I could actually, because all these sides are congruent, I could actually draw, right, since that means the distance from here to here is going to be the same, here to here is going to be the same, here to here, here to here, here to here, and here to here, right there. Okay. I could actually draw basically a circle around this guy. Okay, and I'm gonna try and draw this as best as I can, but Mr. Kiefer's not exactly great at drawing circles. Okay. Okay. I could draw a circle, and this thing could fit exactly in where all of my vertexes are going to touch. Okay. That would mean that each one of these lines that goes from the center to a vertex, right, is what we call a radius. Okay? It would essentially be the same thing as a radius to a circle. Okay? Now, again, that's great, but so what I'm going to do now is, so I've got this thing as a circle, and essentially what I've done is I've gone, okay, you know what? I've actually got, if I think about it, I'm going to draw it in blue, I've actually created as well all these little triangles in here. Okay? we know what the length, or we know how to find the area of a triangle, right? We don't necessarily know how to find the area of this hexagon yet, but if I instead break this up, and remember this is a regular triangle or a regular polygon, so that means I've got all of these triangles over here are congruent. Okay? Because all of these lengths are also congruent. Right? And remember, all these sides are congruent. So essentially by side, 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 I have 6 congruent triangles in here. Okay? And again, that's going to work for any polygon. If I think about this pentagon over here, if I tried to do the exact same thing, right? Because this is a regular polygon, I have 5 congruent triangles. Okay? If I think about this octagon, how many congruent triangles do you guys see in here? An octagon, how many would you say there are? There's 8, right? So basically, in a way that we're kind of thinking about this is, you know what, if I find the area of this triangle, right? If I find just the area of one of these little triangles, and then multiply it by the number of sides, right? I'm going to be able to get the area of this whole thing, right? Yes? It's a nonagon, sorry. I cannot count. Mr. Kiefer is just off today. Sorry. My apologies. Okay. Okay, so there's a 1, 2, 3, 4, 5, 6, 7, 8, 9. You're right. Okay, it's a nonagon. I apologize. Okay. But either way, it's still gonna the idea is still gonna work out the same. Okay, if I find the area of one of these tiny little triangles, I can essentially find the area of the whole thing. So the idea behind this, and I'm gonna erase these for now, because again we're working with the hexagon over here. Again, the idea behind this is if I take the area of the triangle and multiply it by, I'm gonna write it like this. The area of the hexagon, right, is going to equal the area of one of these little triangles multiplied by the number of sides. Okay? Well, let's just kind of remember, what's the area of a triangle? Come on, guys. What's the area of a triangle? What's the formula for the area of a triangle?
Base times height times 1/2.
All right, 1/2 base times height, or base times height divided by 2. Okay, so I can rewrite this as, since my base over here is this S, we're just going to use S for the base, because each of these triangles, right, we could either use the radius or we could use the side. For the sake of this, we're going to use the side for my base. Okay, and you'll understand why when we get to it in a second. Okay, so then that means if we want to think about a formula for finding the area of this thing, it's 1/2 S times height, right? But if I look at this triangle, right, the height is not any one of these radii. Right? The height is actually the segment that goes, so just like this one over here, it's the one that goes from the vertex perpendicular to the base. Okay? And you'll understand why in a second. We're actually going to call this A. Because we're going to say that has a length of A. And I'll explain why in a minute. Okay? So realistically, the area of this little triangle here is S times A. And then that whole thing is times the number of sides. Okay. Well, we already said that perimeter is the number of sides times the length of each side. So a way that we can think about this is simply just 1/2 the perimeter times this A. Okay. And so again, that's kind of this idea. Now this A, the reason that we're using A, right? this segment that goes from the vertex perpendicular to the other side and essentially meets at, and again, we'll kind of find this out in a second, this meets at the actual midpoint of this side. Okay? And the reason why, again, so I'm going to look at this example just to kind of show you. When we look at this triangle, we know that this side and this side are congruent. Okay? And we know that this side is congruent to itself. And it meets down here at a right angle. Okay? Which means that this is also a right angle. So by hypotenuse leg, these two little triangles are congruent, and therefore these sides are congruent. So essentially we've just shown that this thing meets at the midpoint. Okay? Now this segment right here has a very special name, and the reason that we gave it A is this segment right here is called an apothem. Okay? And the definition of an apothem, an apothem, sorry, there's like two different ways to pronounce this thing. I've been saying apothem for years, but I've found out just last year it's apothem, even though there's really debate about that. So the apothem is a segment from the center of a polygon perpendicular to its side. Okay? That's what the definition is. Okay? It's a segment from the center of a polygon perpendicular to its side. Okay? Now, consequently, that means that it meets at the midpoint if we're working in a regular polygon. Okay? And I know you're probably going, oh, what does all this have to do with that? Okay? So basically what we've shown right here, right, in this piece right here, is in order for me to find what the area of any of these polygons is, okay, all I need is the length of a side, the number of sides, and the apothem. I only need three things in order to do this. Okay? No matter what. I only need three. Okay? Now again, if for an example I'm just given the perimeter instead, right? If I already know what the perimeter is, then all I really need to find is the apothem in order to actually solve this. Okay? So I'm going to erase all of this junk over here. Well, not junk, but erase all of this over here because now we've just figured out, okay, that in order for me to find the area of this hexagon, I need the apothem, which is right here. And then I just need the length of one side because we already know that n is equal to 6. Okay? So far for this part, for the area of the hex, I know that this is going to be 1/2 number of sides, which is times 6, times my apothem, which is 5 rad 3, times the length of one side. Now this is where the hard part comes in. Finding one of those missing pieces. Okay? I've got two of them. I've got the number of sides and I've got the length of the apothem. How, and again, just looking at this figure, how in the world am I going to find what the length of this side is? Okay? Or, in even similar to the case after, right? How would I find A in that case? Okay? So here's how we're going to do it. So what I'm going to do now is I'm going to take a closer look at that triangle. Okay? Because that triangle here is really going to tell me a lot of information because, again, we just spent, gosh, how many weeks working with triangles, right? And we just did trigonometry, which is this study of triangles. So there's lots of ways that we can find out parts of triangles given just the minimal number of pieces, okay? So I'm going to take a closer look at this triangle over here. Oops, sorry, that was terrible. I know that the length of this side right here is 5 rad. Oops, sorry, that, you probably can't see that very well. The length of this side is 5 rad 3. Okay. Now, what else do we know? We know it's got a right angle. Okay. We know that this piece and this piece are the same. So let's just say I call this side x. Then I know that the length of, then the length of this side is 2x. Okay. But we kind of need to figure out, right? We need to figure out some other piece in here. We can't just do this with that. So here's where where our trig kind of comes into play. Okay, so I can actually find out the measure of that whole angle right there. Okay. So another way of looking at this is in example number 7. I can find that whole angle. And here's why. So if I draw my triangles, now we know all the triangles are congruent, right? Which means this, we'll call it theta, is equal to this one, 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 is equal to that one. And what do they all equal?
12.
They equal what?
12.
How do you get 12?
Because they're all equal, so that's...
Oh, no, 12 is the length of this side right here. We're trying to find theta. Okay. How would I find that? Well, what do all of these add up to be? Remember how we kind of started, how we even found each of these things. We drew a little circle in here, right? And if I draw my circle, we notice that each of these guys is a central angle. Okay. But since we know that all of these pieces are equal, I know in order to get this central angle, all I have to do is take 360, because I know they all have to be 360, and divide it by the number of sides. In this case, it's 6. But if we look at our nonagon, we see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9. If we look at our pentagon, we see there's only 1, 2, 3, 4, 5. Okay? So in order to find the central angle, okay, and so this is another part. Central angle is always going to be theta is equal to 360 divided by the number of sides. Okay? So again, you're probably thinking, All right, well, how does that help us? Well, in the case of a hexagon, right, the number of sides is 6, right? So for this case, theta, so this whole angle right here is theta, is going to equal 360 divided by 6. Well, what's 360 divided by 6? Come on, guys, that one should be easy. 60. Okay? So again, just focusing on this triangle. We know that this whole angle, right? So again, I'll use a different color for the whole, actually, yeah, I'll use green for it. All right, hang on. What the heck? This whole angle right here is theta, and theta is equal to 360 divided by 6, which is equal to 60 degrees. Okay? Which is kind of cool, right? Because in a hexagon, this is why we're looking at a hexagon, right? That means, since we are, that means we actually already know that this thing's going to be an equilateral triangle. And the reason why we know that is because if this side and this side are congruent to each other, that means that this angle and this angle are congruent. Well, if this is 60 and I know these two are equal, right? All that's left is all that's left is 120 degrees between the two, because remember, interior angle, sum of a triangle is 180. That means that each of these guys are 60 degrees. Okay. Now, it's not always going to be this nice. So, for example, if we're looking at our nonagon, right? Our nonagon, if I look at each of these angles as theta, theta is going to equal 360 divided by 9, which should be what? I think it's 40. No. It's 40. Yeah, it's 40 degrees. Okay? Which means that if this angle is 40 degrees, right, that means, and these are, again, isosceles triangles, that means that each one of these is 70 degrees. Okay? So it's not going to be all nice and neat like our equilateral. Okay? But what I can do from here is I recognize, well, this is a right triangle. The right-hand side is a right triangle. And I know that this angle down here is 60 degrees, which means, what does this angle right here have to be? Anybody? It's got to be 30 degrees. Okay? Which means that this triangle right here is a 30, 60, 90 triangle. And it's very simple for me to use my tools here to figure out, okay, if that's a 30, 60, 90 triangle, right? I know that this length, if this length is x, this length is going to be equal to 2x, and this length is going to be equal to x rad 3. Okay? So if 5 rad 3 is supposed to equal x rad 3, then I know if I divide both sides by rad 3, I know that x is going to equal 5. And so half of my side length is 5, which means my entire side length is 10. Okay? Zooming out means that over here, this whole side length is equal to 10. Okay? And again, for the nonagon, for instance, what you're going to have to do for this one, and again, I'm going to and the same thing with the pentagon, right, is, hold on, if I know that this is 40, right, and I think about this triangle, right, I know that this is going to be 20 degrees here, I'm actually going to have to use trig, remember sine, cosine, tangent, in order to find the missing sides. Okay, so you may have to use trig, so please remember. So, ka, toa. Okay. Again, so now, again, I know that's crazy because that was all that work just to find the length of one side. But why that's nice is because now that I've got that, because again, you might have the side, and for example, on number 6, I've got the side. I need to find what this length is right here, right? I'm going to have to use trig in order to find it, okay? But why this is nice as far as our formula is concerned is, again, area of the hex, and again, we're going back here. I know it's equal to 1/2 times 6 times 5 rad 3, and now we know our side length is 10, so the area of the hex is equal to 1/2 6 times 5 rad 3 times 10, which is going to equal, if I multiply all that together, so it's 6 times 5 is 30, times 3 is 300 rad 3 over 2, or 150 rad 3. Okay. Does that make sense? Okay. So I know that's kind of a lot. So remember SOHCAHTOA? Remember what the definition of an apothem is? Remember what the central angle is? How to find it? And then the area for a regular polygon, right, kind of the big thing here is area is going to equal 1/2 the number of sides times the length of one side times the apothem, or the area is going to equal 1/2 the perimeter times the apothem. And all of that just to develop that idea. Now the problem is each polygon presents its own problem. Okay? And because the central angle is not always going to be nice and neat and form this awesome triangle, but this awesome 30, 60, 90 triangle. But that's why we use hexagons a lot. Okay? All right. Any questions on this? A lot of work just to find that the area of this guy is 150 rad 3 units squared. Any questions? All right, so I will also be posting the solutions for this on Canvas after I post the video and post these notes. Okay. Any questions? All right, so you guys have your assignment today. Please go ahead and get to work. I'm going to stop recording.